Hey everyone, my name is Samuel Olatunde, and the topic of my research is a comparative study of two matrix multiplication algorithms under the current hardware architectures. I did this research in the summer with my mentor, Dr. Eduardo Cominares from Midwestern State University. We started by defining the matrix, we talked a little bit about matrix multiplication, we talk about the algorithms we evaluated in this research, talk about some applications of matrix multiplication, the goals of the research, and the results. What is a matrix? It's essentially a table of numbers. So we have rows and columns of numbers, and we normally represent a matrix by the dimensions. So the number of rows multiplied by the number of columns. So for example, the picture we have here, we have a 3 by 3 matrix because we have 3 rows and 3 columns. What is matrix multiplication? It's a binary operation that combines two matrices together. That's where we get binary from. So essentially, you multiply two matrices together in a certain way. And the necessary condition for this to work is that the number of columns in the first matrix must be equal to the number of rows in the second matrix. Some properties of matrix multiplication: it's not commutative, so A multiplied by B is not necessarily equal to B multiplied by A. And another property is the dimension property, which is if we have a matrix A that is an I by J matrix, so I rows by I columns, and we have another matrix B that has n rows by n columns, the dimension of the product is I rows by n columns, so I by n. Two algorithms we evaluated in this research is the dot product algorithm and Strassen's method. The dot product algorithm has a lot of names. It's also known as the naive algorithm or the traditional matrix multiplication algorithm. So I'll use all of them interchangeably in this presentation. The dot product algorithm is what most of us see in our lifetime. So it's essentially, the way I like to think about it is that we have two vector windows. And we have the first one sliding down the first matrix and the second one sliding across the second matrix. And at every point at every step in the algorithm, we find the dot product between those two vectors. So for example, to calculate the first element of the product matrix in this example, we will take the dot product of these two highlighted vectors. So 1 multiplied by 7 plus 3 multiplied by 2, plus 2 multiplied by 9 and 3 multiplied by 11. We add it together, and then we find our answer. One thing about this algorithm is that it has a time complexity of big O of n to the power of 3, which is a lot. So it increases a lot as the size increases. Another algorithm we evaluated is Strass's method, and it comes from the divide and conquer approach of the traditional matrix multiplication algorithm. And essentially it divides the two matrices we're trying to multiply into 4 equal parts, and it combines the smaller parts in certain ways to produce the final matrix. So the way it works, the way it saves us time is that it's just theoretically expected to save time because it reduces the number of multiplications from 8 to 7. Remember, multiplying 2 by 2 matrices, and as we go bigger, it's kind of that saves a lot of time. So essentially, you bring the time complexity from big O of n to the power of 3 to big O of n to the power of 2.8. Some applications of matrix multiplication: it's used in solving linear systems, it's used in neural networks, it's used extensively in artificial intelligence. It's using population modeling and data encryption and animation and in geology. It has a wide variety of uses, but this is just a small subset of it. The goal of this research was to implement both algorithms on the CPU and the GPU, and we wanted to compare the performance, between both algorithms. So we want to see how each algorithm performed in respect to each other, and also we wanted to see how both algorithms performed on the CPU versus on the GPU. So what is the one big similarity we have between the CPU and the GPU is that they both execute instructions. And the main difference is that the GPU executes instructions in parallel, while the CPU executes instructions sequentially. And a good way to think about it is that the GPU is a specialized CPU, and all the major difference is that it has a lot of workers to process data in comparison to the CPU that has, in a sense, just one worker. So when you have a lot of workers compared to one worker, you kind of guarantee to finish the work faster when you have more workers available to you. The first hypothesis we had in this research is that the GPU implementation should be faster. So we're expecting the GPU to accelerate, the computation, and we also expect the Strass's algorithm to start pretty slow, but eventually peak up and surpass the dot product, so outperform the dot product as we get bigger data sizes. 3 evaluation metrics we use in this research is the execution time, the speed up, which is basically how fast the GPU accelerates the CPU code, And the last one is the ratio of the naive to Strassen. So if the Strassen code is faster than the CPU code, then the naive code will have a value greater than 1. If not, we have a value less than 1. So this is the speed up table. So we have the size, by the number of threads. So the size, we use a square computational grids and square matrices. So we tested the code on square matrices, right? And so, for example, we have 256 by 256, 512 by 512, and all that. And what the numbers in here essentially show is that the GPU code does accelerate the CPU code significantly. So let's pick a specific column. Look at this column here. We have the naive, and this on the right side we just have the number of workers, right? And we see that as the number of workers increase, we can see that the speed up increases, up to a point, and then it reduces. So this right here confirms the law in parallel computing that you can accelerate code up to a point. Beyond a certain point, you don't have a whole lot of improvement. And we see the same trend in a sense, with other data sizes, that as the more we go, we just, we see that, as we go bigger, we see more speed up. So the GPU code performs better than the CPU code. And this is a graph of just one of the data, a subset of the table we have. So we just have, the naive algorithm in comparison to the Strassen algorithm. And what I really want to show is just emphasizing what I said before. If you look at this, we can see that it accelerates pretty fast in a sense, and it gets to a point and it stops accelerating. So this is what we call sublinear speed up, because, initially it's fast and it gets to a point and it just levels off or starts to reduce. This is the ratio of the naive to the Strassen, essentially saying how fast the Strassen is in comparison to the naive code. And you can see that initially with smaller data sizes, we start from like a 0.9, which means it's not faster. But as we go down, we see some improvement. But on this column here, it just essentially just pretty low. But as we go down, as the data sizes increase, we see more promising values. So here, for example, we have a 2.37, which is essentially means that the Strassen code is 2.37 times faster than the naive code, so which is pretty good. And it doesn't stay, as high as that, but we have values greater than 1. So essentially asking the question of whether or not, Strassen's algorithms outperforms or is faster than the traditional algorithm. So the main conclusion we had in this research is that the GPU code does accelerate the algorithms, and it does a pretty good job of that. And another conclusion we had is that the Strassen algorithm gets faster as the size increases. Right now, we are currently furthering the research. We're currently furthering the research. We're testing the code on a better cluster, and we're trying to implement it with bigger data sizes to see, the trend as we get bigger, and see that if that trend continues or even improves and all that. Thank you so much. Any questions?